Hello everyone, welcome to the second part of this introduction class here, environmental point clouds, and we are going to talk about basic concepts of photogrammetry here. And this is a workshop organized by the University of Rennes and the University of Potsdam. So the idea for the next 30-40 minutes is to look at some basic concepts of photogrammetry with a specific focus on geoscientific applications. In the previous presentation, we looked at LiDAR data. We looked at some spatial terminologies, how LiDAR data are being collected, how you turn a full waveform point cloud into a full waveform LiDAR data set into a point cloud, and we looked at some examples and applications. Now we are moving away from the LiDARs and we are going to look at stereophotogrammetry, and we are going to look at how we can use stereo vision methods to generate point clouds from overlapping imagery, how structure from motion helps us to calibrate a camera and orient a camera, and the following bundle adjustment then allows us to optimize the location. Disparity map is a process that measures the offset between features, and that allows us to generate the depth or the dense point cloud that you are likely familiar with. And last but not least, I'm going to show some examples. Again, this presentation is fairly dense, and we would be very happy to discuss or answer questions during the Q&A session. Let me start out by showing one of the often and widely used image here, the concepts of LiDAR and structure from motion point clouds. This indicates the different types of point clouds that are being used in the geosciences. So we talked about airborne LiDAR and somewhat terrestrial LiDAR in the previous class, and now we are going to look at structure from motion and multi-view stereo approaches that use overlapping images. Here is a balloon shown, a helium balloon that was back in the good old days when helium was still affordable. And nowadays you mostly use drones because they have become more affordable. So if we are going to summarize and synthesize some of the LiDAR points, then we know that LiDAR, regardless if it's an airborne or terrestrial LiDAR scanner, works in densely vegetated landscapes. It uses time of flight measurements to determine distances, and you need very good GNSS and inertial measurement units to correct for the airplane position. Some LiDAR wavelengths also allow bathymetric measurements, and I'm certain we are going to hear much more about this from Dimitri. The advantage of LiDAR is that you can have a very small beam and a very large beam, and these are different applications specifically for vegetation remote sensing. Usually LiDAR devices and instruments are expensive, and they're also sensitive, which means you need to be careful with them too. Often LiDAR devices require some kind of a calibration, or at least it needs to be maintained very carefully. If we compare this to photogrammetric approaches, photogrammetric approaches usually rely on much more affordable hardware. And when I say affordable hardware, I mean optical devices that range from a couple of €100 to maybe a couple of €1,000, depending on what you are investing in the optical sensor. Drones are fairly affordable now too. You can even use your mobile phone to collect images and perform measurements with them. The structure from motion point clouds rely on precise camera locations and camera parameters. So the better your optics, the better your results, or I should say the better you have calibrated your optics, the better and more precise results. And usually structure from motion is bundled with multi-view stereo. That is a process that generates a depth map, a disparity map, but very often you just say structure from motion and you drop the multi-view stereo, although that is an important point of it, because these are fundamentally different processes. If you want to have colored And very dense point clouds, you need to have an optical, or you could use an optical device. And photogrammetric approaches allow you to do color point clouds, but also orthophoto generation. Keep in mind that, and I'm going to repeat this several times because it's really, really important, photogrammetric approaches are no lasers. There is no penetration through vegetation. You're only mapping the surface, unless you really can see through the vegetation. Because of optical artifacts and because of the uncertainty in the drone position, you often have warping artifacts. These can be mitigated by collecting ground control points. That's one of the basic assumptions that you make for a precise survey, that you have ground control points collected, for example, with a differential GPS or laser towed station. Some additional points here. So photogrammetric point clouds are definitely affordable, but they can, or they're prone to generate less precise point clouds if you don't know what you're doing. So in order to generate precise point clouds through photogrammetric approaches, you need to work carefully and also calibrate your devices very carefully. You can generate very, very dense point clouds, and I'm going to show some of those, but they often require many photos per square meter and likely some post-processing. So let's look at an example here of a dense point cloud. This is a structure from motion point cloud generated for the campus GOLM. You see the very, very dense and continuous, almost continuous feature here, but you also see that there is a little bit of noise bumps here and there, and this is very, very typical for a structure from motion point cloud, and filtering is required. That's something that we are going to look at some point. If we are comparing this to a Lidar point cloud, this is exactly the same area, but a Lidar point cloud, you see the nicely oriented beams perpendicular to the flight direction. You see that those looks cleaner, but there are also definitely fewer points. This is an older Lidar point cloud. Newer generations point cloud likely would be denser. So there are clear differences between the dense structure from motion point clouds and Lidar point clouds. With the photogrammetric approaches, you can add hyperspectral cameras. So you're not bound to RGB, red, green, blue, the visible spectrum of the light, the visible part of the spectrum of the light. You can also use hyperspectral cameras, and that allows you to provide additional wavelengths and add multiple colors. And here's an example of this, first showing you an airborne Lidar intensity file of the greater University of Potsdam campus. And for that very same area, we used a multispectral camera to generate an NDVI hyperspectral point cloud. This is not a hyperspectral point cloud, but this is a multispectral point cloud that clearly indicates that we have NDVI measurements. The greener parts are more vegetation. This is just at the beginning of spring. You see the roads have a very low NDVI value with the reddish colors, but then you see the individual trees have a higher value. So every point that you see in here has its own NDVI value. So that's a big value that you can have with multispectral cameras. Drone-based approaches or structure from motion-based approaches are usually reasonable for hectare-size study areas. So in other words, when you have a 1 by 1 kilometer area, or maybe even a little more, drone-based surveys are reasonable. If you end up having a 10 by 10 kilometer area, then you likely would like to use different methods, because the amount of data that you have to collect and the difficulties in the logistics for these is fairly high. Keep in mind that drones, at least in Europe, you have to fly a drone in the line of sight. That means usually not further away than a couple of 100 meters, so you could not fly them for longer distances. So for a hectare-sized study area, it's reasonable. For larger areas, not. And I'm repeating myself, but I want to make that point really clear. Structure from motion does not use laser pulses. So you don't have multiple returns. You only have a single return of the point that can be seen on both images. And that also means you cannot see through vegetation. So let's dive into stereophotogrammetry a little. I need to say up in front that stereo vision is a very wide field, and we could spend a whole week just talking about this. This is a very, very, very short and condensed version of it. It's more a conceptual approach, and it does not contain any details of the underlying algorithms. So the question that I'm trying to answer in the next 20 minutes or so is how we can generate point clouds from overlapping imagery. So we first look at traditional photogrammetry, and then we are going to zoom into structure from motion. Structure from motion is the step where you identify matching key points between images that allow you to better and more precisely calibrate your camera and determine camera position. And the second step that you usually apply is multi-view stereo, or the densification step, where you're calculating the disparity or the offset between the different view angles that you have collected before. Those usually go along. Sometimes when you have a very well calibrated stereo camera, you don't need to do a structure from motion approach. You can go directly to the multi-view stereo approach. Okay, I pointed it out before, but computer vision is a fairly dense topic, and this is actively being developed. There is a lot of active research going on in that field, and there are new methods being developed as we speak. The second point that I would like to make is that we in the geosciences don't need to use all of the computer vision methods because they are mostly optimized for real-time measurement, for example, for autonomous driving. Those are approaches that are designed to be very, very fast, but maybe not the most precise one. Because you can think about it this way: you need to identify an object while you're driving, and it does not matter if that object is 100 meters and 5 centimeters away, or 100 meters and 6 centimeters away. But if you're doing geosciences, and if you're interested in geomorphic feature identification, that centimeter can be very important. Or, you can scale it up to different scales, but the point is that we are more interested in a more precise approach, but maybe in a less dynamic approach, unless you are observing a debris flow while it is active. Okay, traditional photogrammetry. In very simple words, traditional photogrammetry takes images at the same height, same orientation, facing nadir, downwards, same camera, and in clearly defined, usually distances. So that means that you have a very well aligned camera geometry that is looking straight down. Using this, you can make many assumptions, and you can use collinear and parallax approaches to determine points on the surface. You're essentially generating triangles between one camera and the second camera, and a key point identified on the surface. And because you're looking at it from two different directions, you can measure the height offset between those different views. I'm not going into further detail here, but traditional photogrammetry is not what you do with structure from motion. A typical structure from motion and multi-view stereo workflow requires that you perform a photo alignment. Let's assume that you have a drone data set that has been collected. The first step is to identify type points, common points between the images, and you align those photos based on those a couple of 100 or thousands of points. I'm going back here for the traditional photogrammetry. If you have aerial photogrammetry, you usually end up collecting or hand clicking 8 to 12 markers and type points per pair. That's much fewer points than you identify via the structure from motion method. And the second step is bundle adjustment, where you take all those key points and you are performing a matrix optimization for location and camera calibration. I'm going to talk about this in a second. And the last one is the last step that you're doing is a point cloud densification. So before you can do point cloud densification, your photo location and your camera needs to be precisely calibrated. And this is happening in those first two steps. And once you know your camera position very precisely, you can essentially measure the offset between those two images, and that's then the depth map or the disparity map that you are generating. Where did it all start? The structure for motion method has been described already in the mid-late 70s. This is the original paper here from Steve Ullman, the interpretation of structure for motion. In October 1976. So this is the idea that you can reconstruct 3D structure. So the 3D is what you call structure through motion, meaning that you can move around in space, and you collect 2D images, and by adding those 2D images together, you generate a structure. A structure is a 3D field in that sense. So this is the description here, and the idea behind that approach is that you identify key points in your image, and you see the same points in multiple images. So the images are highly overlapping. They are also often recorded in a convergent geometry. So you see the same point on multiple images, and if you not only have a single point, but thousands of points, you can identify the camera position, because there is only one location where the camera where the bundles merge, where the camera can be located if you have the 3D information. So you're solving a matrix at the same time for the 3D position XYZ, for the camera distortion, and also for the camera location. So these are many parameters that you're trying to solve, and there are issues with solving such a weakly defined matrix system. So the idea is automatically identifying key points on your image, because for the structure for motion principle to work, you need not 5 or 8 hand click points, you need thousands of points. And an example for this is using the SIFT, the Scale Invariant Feature Transformation. That is an algorithm that was developed in the late 1990s. There is a patent from 2000 to 2020. The patent expired, and now that SIFT algorithm is publicly available, but there have been done many improvements which are under new patents. The basic idea is that you are that you are scaling your images into different grid sizes, and that you're using a Gaussian or Laplacian smoothing that allows you to identify features at different scales. This is an example of a parking lot where features have been identified. You see a bunch of blue points and a bunch of gray points. All of those points are SIFT features. The blue points could be linked to another image, where the gray points did not find a corresponding point in a neighboring image. I wanted to show you the next image. That's the typical drone flight. You see that this is the first image. The drone is moving, collects the second image, and all of those points that you see in one image gets also located or can get located in a second image, and that allows you to link the location of the drone, but also the relative location of the image. So what you can envision is that each of those, I should have been more precise, each of those SIFT features that you see here essentially is a ray that you can envision goes from your camera through the lens to your object, and these form a bundle because you have thousands or hundreds of rays, and you would like to optimize these rays, and this is what is called the bundle adjustment. So these bundle adjustment then optimizes for the potential distortion in the camera, but also for the camera location. And that distortion is really, really important because you have often deviations of several pixels or even more for optics. This is a view showing a distortion plot. You see on the x-axis image pixels, 4,000 pixels. On the y-axis, the 6,000 pixels. So this is a 24 megapixel camera. 6,000 times 4,000. And what you see here are contour lines of offsets of pixels. These have been generated by carefully calibrating a camera with a Charuko board or a chessboard. You can use that as well. And you see that each contour line is a roughly 1 pixel offset. So this is the center point. Here you identify for this camera a 2 pixel offset. You would need to correct the pixel location by 2 pixels. That's what the camera calibration tells you. And usually it gets higher distorted into the corners just because of the aberration of the optics that you end up having. So the point that I want to make here is that you can have 10, 12, or sometimes even 30, 40 pixels distortion in the corners, and you need to be able to correct for them. Because if you have a 40 pixel offset here in this corner and you're linking that SIFT point with a point that is somewhere in the center, that point would be 40 pixels away. So your camera location would be different. So it just makes this point, I just want to make this point really clear. So if you have the same point, if you have the same point that is further towards the corner, for example, this car feature here, and the camera is distorted, those pixels would be 40 pixels away, for example. Whereas you're trying to link it to a part of a next picture where you have less distortion at that XY image pixel. So it's really important to have that camera distortion nailed down. Otherwise, your SIFT features cannot properly linked, or in the end, you have a much more noisy point cloud. After the camera calibration, the bundle adjustment, you can generate your depth map or disparity map, and that is also the point cloud densification. So this is a typical disparity image where you see the offset between two images. The color indicates the offset between two images. How many pixels you need to move one image to match it. So the ground has a fairly same continuous color because you don't have to move the two images against each other. This is a top-down view. Whereas here along the buildings and along that roof here, you clearly see that you have to shift the one image versus towards the other one a much higher amount. So this is a depth map, and you generate those depth map for every image pair. So when you have 50 images, you determine how many overlapping views you have, and you can then get quite a few overlapping images of the same point. So it's not only the adjacent images that you generate depth maps for. You usually end up with hundreds of depth maps for a general drone survey. And then each of these depth maps is being transformed into a point cloud. Each of those depth maps, you have X, Y, Z coordinates. So each of those if you have one depth map, you automatically have a point cloud. And you end up getting a very dense point cloud because you not only have one depth map, but you have several depth maps that end up being overlain. Sometimes, if you have worked with structure for motion point clouds, you realize that there's a little bit of noise above and below a surface, and this, for example, stems from a bad alignment between two images. You can have sometimes one or a couple of images that didn't get well aligned, and then you end up producing a much more noisy point cloud. Okay, let's look at the last part here, some examples and applications. And this is a mix of some new development and some examples that are likely of interest to the audience. I'm stressing again the importance of camera calibration because I too often see that data are being acquired without properly calibrating your camera or without collecting ground control points. So this is a top-down view of a building, and you can clearly see the curved feature of this building. This is not a modern architectural building that is actually curved. This is a straight building. The reason why this is being curved is because the camera optics is being has some aberration in it. So this is a clear example why you would need to do camera calibration. You see the curved building here, you see the curved building here. This is something that requires camera calibration, but the good thing is you can do the curved features. This is not a bad thing. You just need to properly calibrate your camera. That's the core point. You can solve that problem. Another point that I want to make on the right-hand side here is that modern drones allow to have a differential GPS sensor that adds the geotag, or that adds a more precise position, or that allows to use post-processing and then provides more precise position. This is a really useful that's a really useful thing to nail down your position, because that then helps during the bundle adjustment process. We made some tests with a couple of different drones, and we identified that this differential GPS sensor that can be added to many drones is a useful addition and ends up producing reasonable results. But you still get better results by having a dozen ground control points. That is still a much better and more precise solution. I talked about ground control points. What are ground control points? Ground control points are features that can be automatically identified with processing software. These are typical features that can be recognized in typical software. We place them on different buildings on the university campus, and we are calibrating our cameras using these markers. You can also place those markers in the field. This is a typical large printout. You collect the differential GPS position from the center point, and then you use that to constrain camera calibration during the processing. Of course, you can also use, or if you have at your disposal a differential GPS station, it certainly helps. A GPS station with a short baseline certainly helps. So why am I telling you this? The reason is that it is fairly often that optical derived data sets contain a doming or a dishing effect. This has been very nicely described in a paper by James and Robson, and describes how this doming effect can be mitigated, and what the reason for this is. And I just wanted to point out that the doming or a dishing effect can be several meters in magnitude, or even more. It depends on the size, and it depends on the camera calibration that has been done. So the reason for the doming effect is that you're trying to solve for camera calibration and camera position at the same time, and if neither one is well constrained, then you are propagating uncertainties that lead to doming effects. So either better constraining camera position, for example, through a differential GPS, or by changing flight geometry, by adding a different range of flight geometries, you can mitigate some of these effects. But the safest part is always collecting ground control points. That's the best quality control that you can do. So here's an example of such a dishing effect. This is out of Cloud Compare, and this shows the difference, the height difference between a structure for motion point cloud here collected with a Mavic Pro, a newer model. This should be May 7th, 2020, not 2000. So this is almost 2 years old. And this is the offset in meters. So in the blue area, the structure for motion point cloud is 1.5 meters lower than the airborne point cloud. And the red points here are 1.5 meters higher than the airborne point cloud. So this is essentially a dish that sits in that point cloud here. And that's a feature that you would like to remove. So you can fit a sphere to it and remove this, or you can provide ground control points. That's exactly the same data set, and we added 8 differential dGNSS ground control points that helps you to mitigate some of this process. So the scale here now is from minus 25 centimeter to plus 25 centimeter. There is still some spherical object in here, but or pattern here, but it's definitely has become less. So this is a typical example of how you would mitigate the doming dishing effect by adding differential GNSS points. I pointed out before, you get reasonable results with a differential GPS sensor on board your drone, but you're not fully able to get the largest or highest precision. So you still would want to add a bunch of differential GPS points collected on the ground. Another example that I would like to show here is that you can shift scales too and look at very detailed pebbles. So these are small scale features, roughly 3 centimeters in diameter. These pebbles, in order to generate that point cloud, we have collected 30 to 50 images, and you can see that there was an issue with some of the alignment issues. You see those noisy parts that exist here that are usually derived from a couple of images that are not well aligned. So the question is what can you do with this? We have been using photo sieving techniques in the past to identify grain sizes from orthophotos. The idea here is to look at the point clouds themselves and, for example, use a curvature-based method to identify the rims or the sides of these pebbles, and then segment these pebbles into separate pebbles, and then perform geometric and volume calculations on those segmented pebbles. So this is a classical problem in computer vision segmentation that has been widely used in the material sciences. The nice thing in the material sciences is that you often have cleaner and clearer data sets and less shadow and less or you often have a more homogeneous data set. So the challenge often with natural or geoscience data sets is that you end up having many other objects in your image. So these were a couple of short examples. These were just thought to provide you with some ideas and background information, and we are very happy to take questions and discuss any of those things in greater detail. Thank you.